Let's try an example of that surface area formula. So we want to, in this example, find the surface area of the unit sphere, and we're giving it the parameterization of sine u cosine vi plus sine u sine vj plus cosine uk. So u ranges from 0 to pi and v from 0 to 2 pi. So if you remember, the surface area formula that we're going to be looking for here is we're going to be switching this to the double integral over D, which is that region in the UV plane, and we're going to take the magnitude of the cross product of the partial derivative vector valued functions. So let's look for those partial derivatives. So let's look for r sub u and r sub v. So r sub u, so we're taking a look at r of uv and taking the derivative just with respect to u. So we've got sine u cosine v first. So that's going to become cosine u. And then the cosine v we'll just treat like a constant, so it will stay attached, and that'll be times I. And then plus sine u sine v, so it's going to be plus, again, sine u will go to cosine u, and then we'll have cosine v just stays as a constant, and then plus cosine u. Cosine's going to switch to a negative sine u. Okay. And then we'll have r sub v. Now we're taking the derivative with respect to v, so sine u is going to stay constant, so we'll have the cosine v is going to switch to a negative sign, so we'll have negative sine u sine v I, and then we'll have plus sine u times sine v is going to go to cosine v j, and then cosine u is just going to be constant, so this is going to be essentially plus 0k. So we could either leave that off or put the plus 0k to be explicit in there. We're going to take the cross product of these two things. Oops. Ru crossed with Rv. So we'll set up that determinant form. So we've got I, j, and k across the top. And then we'll put r sub u first. So we're going to have cosine u cosine v. And then we'll have cosine u cosine v again. Or sorry, I made a mistake there, didn't I? Right here, this was sine v to start with, so this will still be sine v. Excuse me there. So this is cosine u sine v, and then k is negative sine u. Let me make this determinant a little bigger so I can fit it in. And then r sub v, we're going to have negative sine u sine v, and then we'll have sine u cosine v, and then we're going to have just a 0 in the third one. So let's go ahead and compute this determinant. So first we compute the I, so times I, we're going to do, look at the little determinant over here, so we'll end up with cosine u sine v times 0, so really just 0, and then we'll have minus a negative, so we'll have plus, we're going to end up with sine u times sine u cosine v, so sine squared u cosine v, that's all times I. And then for j, we're going to take this outer determinant, so we cross off that middle row and top column, so we're going to end up with minus cosine u cosine v times 0 will just be 0, and then we have minus a negative times a negative, so we'll still get another negative, sine u times sine u sine v, so sine squared u sine v all times j. And then for k, we're going to take this last determinant, so we'll have cosine u cosine v times sine u cosine v, so we're going to have cosine u sine u cosine squared v. and then we'll have minus a negative, so plus cosine u sine u sine squared v, and that's all times k. So then if we take a look at just cleaning this up, so we've got sine squared u cosine vi minus a negative, so plus sine squared u sine vj. And then notice in the k's that we have a cosine squared v plus a sine squared v. So we're gonna, and then we have the same coefficient on both of them, cosine u, sine u. So we're gonna just be left with that cosine u, sine u. We could think about factoring it out, and then cosine squared v plus sine squared v is 1. So now what we need to do is take the magnitude of this. So we're going to end up with the magnitude of r sub u crossed with r sub v, which is going to be a square root, and we're going to take all of these components squared. So we're going to square sine squared u, so it'll be sine to the 4th u cosine squared v, and then plus sine to the 4th u sine squared v, and then plus squaring the k component, we're going to get cosine squared u sine squared u. So then notice with these first two terms, we've got a cosine squared v plus sine squared v, and they both have the same coefficient of sine to the 4th u. So we could factor that sine to the 4th u out, and then it would just be cosine squared v times, or plus sine squared v, which is 1. So we have sine to the 4th u plus cosine squared u sine squared u. And then to help us see this one, let's actually do the factoring. So notice both of them have a sine squared u. So if we pull that out, then we're left with sine squared u plus cosine squared u, which again is 1. So this is really just square root sine squared u, which is just sine u. So then putting that into our integral up top, this is the integral we're trying to look at. So we're trying to integrate sine of u over our domain D, which will be these bounds for u and v. So we can take a look at putting all of that together then. So my integral over d of the magnitude of r sub u crossed with r sub v dA is going to be the double integral of sine of u. Our u bounds were, you can scroll back up and see, we had u went from 0 to pi, and then v goes from 0 to 2 pi. There we go. So we can do a du dv. U is 0 to pi, and then 0 to 2 pi. So then we've got sine u du is going to go to negative cosine of u and evaluate that from 0 to pi. So plugging in a pi, cosine of pi is -1, so negative 1 is a 1. And then we're going to subtract off plugging in 0, which plugging in 0, then we're going to get negative cosine of u, which is 1. So keep track of all of our negatives here. So ultimately in that integral, then we have 2 dv. So this is going to be 2v, evaluated from 0 to 2 pi, which is going to give us 4 pi and then minus a 0. So my surface area of that sphere is going to just be 4 pi. If we were to do this with trying to represent it with non-parametric surfaces, we either would have had to switch it from being a sphere to kind of looking at them separately, the upper half sphere and the lower half sphere, to look at it as functions. We also could have switched to spherical coordinates, which if you actually pay attention to what our parametrization up top was. This actually is spherical coordinates, just with u instead of a phi and v instead of a theta, and then rho in this case would be 1 because it's a unit sphere, which is kind of cool. So we're kind of just seeing it stored in a different way for this example.